Hello everyone, welcome again. Now we will start a new chapter, chapter 13, buckling of columns. First, I want to introduce to what is the definition of the buckling term. Let me to slideshow. Yes, in here we can start. Yes, I'm sorry. Yep. Okay. What is the meaning of the buckling? You can see different to the formation of the line element. You can see, the tension, compression, shearing, torsion, bending terms we have already seen on previous chapter. Now we will start the new deformation type, the buckling. You can see in the right side of our page. And what is the meaning of the buckling? In the buckling is the sudden change of the shape when they are structural, especially when on the structural member which can exposed by the extremely high external load, and also we can in this case our compression member such as column can lose their stability and can pass the unstable stage and high deformation, high vertical and horizontal deformation, lateral deformation can be seen in that column. These sudden change of our column element and vertical element we call as a buckling. So it's the critical point is what is the limit of the load, in which critical load can be past the unstable state, and limit of the load, how we can find this load, especially this is extremely important, and we can find theoretically we can find this load. We call this load as a critical load. Critical load is when the member starts to losing stability under axial loads. And critical load depends on two material properties and shape properties as well. So first of all, how we can find the critical load, I want to introduce. And I want to illustrate a simple, I want to find the critical load simple shape. It is not actual represent the column load, but how we can find P critical. It's a good way to obtain the critical load in this example. And first of all, in order to find the critical load, you can see the shape in A in here, and like this. And after that, and we also we try to draw our shape when these column losing the stability, such as like this, okay, and we drawing shape like this, and we try to draw in point C. Then is the free body diagram. How we can find the free body diagram? That I want to. Maybe you don't understand how we can find this force. I want to do it my camera. For example, I want to draw again unstable case like this, and in the shape we called this angle as a theta. So, and there's some kind of the point load in point. Is there any point defined? Like this point, okay. And if I want to, equilibrium in this point, we have a point in here, and we have some kind of the force P, like this. I'm sorry, I can define as F, sorry. And we have an angle theta in here. I want to write this x and this this one is the y-axis, like this. And sigma fy is equal to 0. I can write f times sine theta minus p is equal to 0. So f is equal to p over sine theta. So also, you know, due to symmetry and also due to equilibrium, we have some kind of p force in here. Therefore, if there is also additional F force in here. So, and also, is there any? Yes, point A. Also, I want to write the equilibrium on point A too. You know, here is the point A. Okay. We have a two force in here. First force is the F. What is the value of the F? F is equal to P divided by sine theta. And one more term, P divided by sine theta. Also this angle, both this angle, be called as a theta in here. Okay. I think I can use different color for theta. It's like this. This is theta. This is theta in here. So is that one more additional force? Yes. Also, we have a, you know, spring available in here, and we can this distance as a delta. So I want to say this distance as a delta. So we have some kind of spring force, which is equal to k times delta. So if I want to equilibrium for fx is equal to 0, you know, we have two force, 2 pi divided by sine theta. So this term is equal to also, actually, I forgot, I'm sorry, I made a mistake. In here is not sine theta, it should be cosine theta. So I made a mistake. Because I know it's the angle in here, I should write cosine theta. Sorry, therefore these terms also should be cosine theta. So this term also should be cosine theta times, you know, its angle is the sine theta. We take the x direction, sine theta minus k times delta is equal to 0. So you can see sine theta over cosine theta we called as a, sorry, 2p cosine theta times sine theta minus k times delta is equal to 0. So 2p tangent theta is equal to k times delta. So first of all, I want to, we have a small deformation theory. In small deflection theory, maybe you remember the from the matter is the when theta is too small, sine theta is equal to tangent theta, and also it's equal to, you know, very close to equal, therefore we call it a theta. So our formulation becomes also in from the geometry, you can see, you know, this angle is we called as a L over 2 in here. For this term is equal to, you know, and L over 2 times sine theta. So delta is equal to L over 2 times sine theta. So also sine theta is equal to theta. So if I rewrite again equation by using these transformations, 2 pi theta is equal to k times L over 2 times theta. You know, we can eliminate two theta terms. So we obtain that P, we call this a P critical, is equal to K times L divided by 4. You know, it's proof that you can see, you know, don't confuse the two mathematical calculations, but it's very simple theory. We draw the free body diagram. Okay, we applying the equilibrium equations such as sigma fi equal to 0, sigma fx equal to 0. In some cases, maybe we can use to sigma moment is equal to 0. It depends on our structural shape. And after that, we apply to small deflection or small deformation theory. And also we define as a theta is too small. Therefore, you know, assumptions we can use this assumption: sine theta is equal to tangent theta is equal to theta, and after that we can calculate this P critical force. Also, I want to make one more practice from using the example 13.1. You can see our strategy is it's same. And also I want to play this part. Okay, find the critical load of this shape. Again, I want to draw the free body diagram. Like, I want the deformation shape like this. Okay, and here. Yes, and I want to define the name of the angles. This angle I want to define is theta. This term I want to define is alpha. This length is the A. This length is the 2A. Okay. Also, I want to, this length is the delta. What is the meaning of the delta? And delta is equal to, I said, A times sine theta. And also, I can see in here, I can see there's the spring in the point. And also, I want to write the point names. This is point A, B, this is C, and this is the D. Also, due to similarity of triangles, you can see this length should be, you know, half of this length. Therefore, that's this equal to delta divided by 2. So I write the geometrical shape like this. Okay. And I think I can write all the geometrical shapes. Now I want to show the forces, calculate the forces. First of all, I want to start with the point A. You know, we have a vertical force of P in here. Some kind of, I want to conclude is the FAB. You know, I call this angle is theta. So it's similar way the previous example. You can see FAB is equal to P divided by cosine theta. So we already find this. And let's continue. Also, we have again one more angle. in here. In point A also, I want one more force, the support reaction force. I want to introduce the AX. Also, I want to find this force. You know, in order to find this force, I can use the sigma Fx is equal to 0. So if I write this force, now I take to left to right is positive AX minus FAB times sine theta is equal to 0. After then AX is equal to P divided by cosine theta times sine theta is then this is also equal to AX is equal to P times tangent theta. So I already find to A, X, and P. Now I need to consider the internal forces. I want to discuss the whole system. Therefore, I don't divide the structures. I want to draw a whole system, and I want to draw the free body diagram. This is our structural shape, and let's start with our forces. And first of all, I want to write the P vertical force in here. And also we have a AX, also value of the AX I can write in here, P times tangent theta. Okay. Also on point C, we have C, Y, and CX support direction. I think CX also should be first direction, like this. Okay. Also one more force available in here. Also we have a spring force is equal to F spring is equal to K times delta. You know, and I already calculate this, sorry, K times delta over 2. You know, our structure shape right here in here. Also this is equal to K times, you can see delta is equal to A times sine theta. Therefore K times A times sine theta divided by 2. So we have also length I can write in here. This is like this. Each length is, this is equal to A, this is equal to A, and this is equal to A. Now I want to take a moment on point C. Okay. I want to delete this part after. Now I don't need this information. I think this is enough for us. So this, okay. Sigma moment MC counterclockwise is equal to 0. Let's start. You can see P does not generate a moment on point C because direction passed through the line C. Additionally, Cx and Cy also does not generate a moment. Just only two forces generate a moment. First one with the Ax, which is equal to P times tangent theta, and this is the moment is P times tangent theta times, moment arm is the 3a, and direction is the clockwise direction, therefore I can write the minus. And also one more force in here, K times 8 times sine theta divided by 2 spring force. Also direction is the counterclockwise, therefore I can write positive K times 8 times sine theta divided by 2 times, moment arm is the, you can see, A, like this. So its total summation is equal to 0. So also you remember that the tangent theta at small degrees and sine theta is equal to its theta we take. So pay theta 3a is equal to k a theta divided by over 2 times a. So you can see this a is disappear. Also theta is disappear, and we can see p is equal to k times a divided by 6, I guess. Let me check the result. Control this. Is it correct or not? You can see, sorry, I need to go back. Go back, yes, k times a times divided by 6. So, and compare with the result, yes, correct. Now we will pass to the new in our real chapter. This is like the warm-up question for you. You know, in this question, we told that for element AB and element BC does not bend, always we thought is straight. But in reality, these structural members can bend. Therefore, we can, after that, we will use a different strategy. So we have simplifications. We have a continuum mechanics in elasticity theory will help us to determine the P critical. So in order to find the critical, first of all, we can discuss the simple element, the simplest element as the ideal column. We call this. What is the meaning of the ideal column? Ideal column is the perfectly straight member before loading, and both ends are pinned. The first end is the roller support, the second end is the pin support, and also load is directly throughout the centroid of the cross section. In other words, moment does not occur in the system. Okay. Also, in order to obtain the critical load, we have an assumption. The material property we call this the linear. Also, we neglect the geometric nonlinearity and also small deflection theory. We assume that, you know, maybe you remember that in previous questions, in the theta is too small, we will use a like similar assumption. So after this assumption, I don't want to prove for you, just only look at on slides. You know, we have a same strategy like the previous examples, but shape is not helpful for us. I want to draw a similar drawings in here, and I want to open my camera. Yes. So for example, we have this system is roller support, okay, and these structures then bend like this, okay, and also not like this, I think that, yes, and this is the pin support in here. I want to take this point, okay. In this point, we have I want to draw a free body diagram, and we have take a section upside in here. You know, we have a point load in here, P, okay. Also, you know, we have a AX in here, okay. I'm sorry, we don't have an AX because, no, I can also prove the AX is equal to 0. I think that is also helpful for us. AX. Also in here, we have take a cross section. And, you know, we have a shear force to V and moment. I don't need to consider the shear force. I want to write the moment. I think moment direction should be not like this, should be like this position. First of all, I try to find the AX. You know, we have a point load in here. Okay. And if I want to write the, sigma fx is equal to 0, there is no vertical force available in this system. Therefore, the AX is equal to 0. So I don't need to write the AX in here. So in here, just only if we take the cross section, we have a vertical force point load. Also, this length is we don't know. Also, I want to write the like y. Okay, what is the y? Y is the deflection. So if I take the moment on point 1, you can see, and in sigma moment 1, I want to take the counterclockwise is equal to 0. P times y minus moment is equal to 0. So you can see, also I can say the moment times Py is equal to 0. So you already know what is the meaning of the moment with different relationship between the moment and deflection. Maybe you remember that. Pi d square y over dx square minus Py is equal to 0. And also if this is a, differential equation, second order. How we can solve this differential equation. Now I don't want to separation of variable. Maybe did you take or not, I don't know differential equation, but we can use the separation of variable in here. I don't want to solve whole system. After solution this differential equation, we obtain these like this solution. We have a two coefficient. In order to two coefficient, we will apply the boundary condition. Is boundary condition, we have a support reaction, and both first and second end, we know the deflection is equal to 0 because pin supports available both ends, therefore the deflection is equal to 0. After applying this boundary condition, we obtain that c times sine pl in square root like this function is equal to 0. So in order to obtain, the first term is the c1 should be 0, but if the c1 if the 0, it means that there is no deflection, all the y is equal to 0. Therefore, we are wondering that this term is equal to 0. This is the trivial solution. This is the real solution. Therefore, this term is not, C1 is not, cannot be 0. Therefore, this term should be 0. After writing this term should be in 0, inside of the parentheses, when the sign is equal to 0, inside of the parentheses should be equal to n pi. So if we subtract take out of the p out of in this formulation, we obtain the p is equal to n square p square ei over l square. So we have how many solutions? Infinitely p solution we have. So which one is the critical? I think the smallest one. What is the smallest one? When the n is equal to 1. So our critical force is equal to, when we put the n is equal to 1, p critical is equal to p square ei over l square. This is the important. We always apply like this question in P critical, Pi over L square. This is the critical load for ideal column. We also, another definition of this P critical load, the Euler buckling load, any type of P value, we can use it. In our question also, it's our critical load. We say this is a critical load. If our P is greater than this load, our structure, we pass the unstable state, but also in our question, also we compare our critical load is the P yield force, the yield force, sigma yield times A. If our critical load greater than yield force, our critical force should be equal to the yield force. Also in the question, we also compare with the yield force. We also compare our critical force and yield force in our questions. Okay, let's start with the example 13.1, and it is not hard. This is very simple question. Therefore, I don't want to use camera and my hand calculation. There's some steel Ch13 or some kind of the steel grade is given, and also structural shape is W shape is given on the figure, and the figure is the used bolt and is the pin. So this is the ideal column, and determine the largest axial load it can support before it begins the buckle or yield stress. So we compare critical force for buckle and yield. Which one is the critical? We will take. I think is the critical one is the smallest one. So therefore we have a critical force for buckle and yield. Which one is the smaller? We will take this value. So also cross-sectional properties of the double section is given. You can see there's in the previous formulation, we have formulation PEI over L square. So in this question, we have a 2I values, 2 moment of inertia values. So which term we will should use? And the answer of the question is hidden in my previous words. I said the P critical is the smallest one. So in this case, which I is smaller? So we will take these values. So we will consider not IX, IY, because IY is smaller than IX. Therefore, P critical for Y direction is much more important, much more critical than the X direction. Also, I can say. Also, yield stress, also sigma Y is given. Why we are using this? You know, we compare with the yield force, and so we need a sigma Y value. Also, modulus of elasticity needed for calculating Euler buckling loads, P critical load. So, you know, I compute with both P critical Y and X values. So, and you can see, I know that we already know it's easy to see. P critical Y is smaller than P critical X because the IY, I'm sorry, I miswrite in here. Actually, I need to finish my slideshow. This should be not, I put the same value. I need to correct it. Term. This is not should be like this value. Okay. Now I want to continue. Okay. So, you know, P critical Y is, we know the smaller than we know the critical X. Therefore, but in question, I compute both P critical X and Y directions. You can see P critical Y is smaller than P critical X. Also, I want to compete with the P yield stress. You can see we have two values. The first value is 1,887 kilonewton. The second one is the 5,613 kilonewton. The third one is the 1,472 kilonewton. So which one is the smallest? As yield is the smallest, therefore our critical force is equal to 1,472.5 kilonewton. So if you forget to compare with the yield force, sometimes we can get wrong answer, wrong results. Okay, in our questions, always we compare with the yield force. Okay. And the question is the new question. If we have a different end conditions, you know, we have compute critical force for ideal column. For we have a different column times. What are the P critical forces changes? For example, I want to discuss the both ends are fixed. How we can obtain this? we will use the same strategy. Now I don't want to redraw and recalculate it, but after that we can apply it like this differential equation. After solution of the differential equation, we found the P critical force is P square EI over 4L square. It is, you can see, it is not same as the Euler buckling load, P critical force, but it is very similar. Just only ratio difference between and P critical elastic load, Euler buckling load divided for 4, just 1/4 times lower than 2 Euler buckling load. So, and also the other types we have a like similar relationship. Therefore, we simplify the relationship like this: P CR for this end condition, P square EI over K times L square. K in this question should be equal to 2. What is the meaning of K? We call this a K is effective length factor. After using this general formulation, you can see different end conditions. We have a different kind of and different terms. Both pinned, we have an ideal column. Therefore, K should be K is equal to 1. Both ends are free ends. Our K becomes 2. For fixed ends, K is equal to 0.5, and also for pin end, K is equal to 0.7. Also, I want to say about the elastic critical stress. This is not new term, I think. Sigma is equal to P times A. Sometimes we are not compute our result with respect to force. Maybe sometimes we need to compute our forces with respect to stress. Therefore, how we can calculate this, especially in the design codes, for example, allowable stress design, we always discuss two boundaries. We always compute our relationship to boundaries with respect to the stress. Therefore, we can convert the critical stress to the critical force to the critical stress. Now divided by A. After divided by A, you can see, you remember that P square EI over chi L square. So divided by A, I times, maybe you remember from the steel course or the other course, and static course, we called as a R square. What is the meaning of the R? R is the radius of gyration. If you include in this formulation, we obtain that P square E over KL over R square. Maybe later you will learn this. K times L divided by R terms we called as a effective length factor. You will see definition of effective length factor. Why we are using we could also symbolize as a lambda. Why is so important for us? Every steel design course, we are always comparing to buckling buckling types by using these termination K times L over divided by R, like this. So, okay, let's start to the new example. Example 13.2, there's some three-dimensional shape. Is 8 meter long. Both ends are fixed. So, top and bottom points are fixed, this shape. And its load capacity is increased by the braces. So you can see, moment of inertia in y-axis is much more weaker than the x-axis. Therefore, in the question, we increase the load capacity by using the bracing. And by y-axis, some of you maybe say that, hocam, direction of the bracing is on x-axis, but right-hand rule. Don't forget the right-hand rule. On right-hand rule, I want to also I can say it, you know, bending on y-axis, bracing axis. We don't need to start with the bending axis. You can see it's like on bending on y-axis, but bending on brace direction on x-axis, but they prevent. And right hand rule, you can see, look at this finger, they show the y-axis. Therefore, that braces prevent bending or prevent buckling on y-axis. Therefore, don't forget to use the right hand rule to determine to bending or buckling side. Okay, so it's it starts to determine the pin connection. So mid connection is the pin. Okay, determine the load it can support. The column does not buckle or nor material exceed the yield stress. Similar to the previous question, we will also control the yield stress and buckling. Which one is the smallest one? We will take this value as a critical force. So I think I want to summarize the question. We have a system like L is equal to 8 meter, but this L is, we have a, sorry, I don't need to write like this. We have a two type of tube buckling and yield. We will control. On buckling, we have a x and y axis. On yield, you know, we have sigma yield times A. So for x axis, we have a length is equal to 8. So we have a both ends fixed. We have a conditions. For y axis, L is equal to, you know, half of the beam. Therefore, I can take the 4. You know, we have a two type of connection. You know, in first type connection, first fixed, second and midpoint is pin. In second part, first pin, second fixed. So we compute how many P critical force. You know, we have a P critical 1 for x direction. This is the P critical 2, P critical 3, and P critical 4. After computing the 4 P critical, which one is the smallest one? Are the general P critical force like this. Okay, also cross-sectional properties, area, moment of inertia, also modulus of elasticity, yield stress, every information is given. You know, we start, first of all, we have to start with the P critical for x-axis. And after that, we found, you can see, both end in fixed, and therefore K is equal to 0.5. After putting the 0.5, we obtain this value. Also, I said on y-axis we have two parts. In both parts, there's a K term is equal to 0. Therefore, also L is equal to 0. Also, we don't need to separate two parts. We can use it just on the formulation for P critical Y. This is equal to 460.8 kilonewton. Also, yield stress also we compute is equal to 1,284.6 kilonewton. So we compare all forces. The most critical one is the P critical Y, which is equal to 460.8 kilonewton. Okay, let's start with the new subchapter, second formula. Second formula, why we are using the second formula? Up to this point, we always discuss with the our force, the vertical force, directly past the center of the cross section. What about if an eccentricity happen or on column? What our result change? First of all, our solutions becomes more complicated. Also, I don't want to make proof in the slide, but I can say to conclude the result, sigma maximum is the yield maximum stress is P over A times B. E is the eccentricity. C R square, the R square. In second, KL over P, like this very complicated function, should be sigma y. And if I conclude this function, P critical like this function. So is it simple or not? I don't know. It is the first term is the so many terms available in this function. The second difficulty is the function is we cannot take out the P critical in one side because the question is non-linear, is closed for a function, a closed equation. Therefore, in order to find this P critical, we can use the different solution type, the numerical computing techniques such as Newton-Raphson bisection methods. I don't know did you take the numerical methods or not, but in order to solve like this question, we can use the different solution techniques. Also, in the question, in this example question, I used the MATLAB and to get result. Also, if I have, I try to solve using my MATLAB. Hopefully, we will get the correct result. The computing, equation is very complicated. Therefore, it is easy to make the computational mistake. Okay, let's start with the example 13.3. We have a column like that in fixed base and braced top on the also fixed. In other words, both ends are fixed. Free to rotate to y axis. So it means that fixed for the displacement, but free to rotate y axis. I mean that on y axis, for x axis the connection is fixed, but for y axis, I think the free to rotate is the pin, meaning that. So one end, the top end is pin, the bottom is fixed. So I think that maybe you're confused. After when reading question, the question say that I want to like the top and bottom, x and y axis. For bottom, both sides is fixed, but on top side for x axis again fixed, but y axis pin. So in this part, so for x axis we take k is equal to 0.5. For y axis we take k is equal to 0.7. After reading this statement, okay, then determine the maximum eccentric load column can support before being buckle the yield stress. And actually, first of all, also you can see for x-axis, also one more term I forgot that. You can see when we look at the shape, P force, take a moment for x-axis or y-axis, and moment occur and for x-axis and y-axis, you can see if I'm using the right-hand rule, for x-axis, there is no, for y-axis, there is no eccentricity because does not moment occurred on y-axis, like this. But for x-axis, okay, we have an eccentricity. What is the eccentricity? 0.2. Maybe you can see that. So you know, for y-axis, we will use the similar formulation like the earlier buckling load like this. But for x-axis, we will use the second formula. So in here, we will use the standard critical load formulation. But for x-axis, we will use the second formula. After that, first of all, I want to start with the easiest one. You can see y-axis, no moment on axial load, k is equal to 0.7. I put to PEI over KL square, and after that, we obtain the peak C critical is 5,136 kilonewton. For x-axis, moment occur, eccentricity is given, eccentricity is equal to 200, and also C is also wondering that what is the meaning of C? Sorry to tell. C is, maybe you remember that what is the meaning of the C in here? Actually is easy to understand too. You remember for bending, sigma is equal to m times EI divided by C. This term is like similar to C. What is this meaning of the C? C is this is a natural axis to farthest distance, the longest distance, the point of the section to natural axis. Therefore, C. So in our section is I section in our question. So and depth is given in the question. So C is equal to half of the depth, or therefore we will take the D over 2 in our question. So I want to go back to our question. So C is equal to 105 millimeter. I'm working with the millimeter Newton in this question. Okay. And you know, our question is very complicated. Okay. And actually, I'm not sure using the MATLAB or not. I think that is a good practice for you, the MATLAB too. Most of you ask me that, Hocam, how we can use the MATLAB in our, we don't have any, appointment with our university MATLAB. In Akdeniz University, there's a MATLAB appointment for PGS company, so we can free to download the MATLAB version, the latest version. But there's also free online version available, MATLAB. I want to write the address MATLAB online like this. Write the MATLAB online, and if you can generate a free account, okay. I'm not, for example, I want to use my university address, but you can use the personal address in here. I hope I remember my password correct. Sometimes I made a mistake. Yeah, this is correct. And click with the MATLAB online and start. And it is actually I want to start with the okay. I have a little bit trouble to use the both slideshow and same times. I want to use two windows at the same time. Therefore, I want to increase the size. Yes, I can see. Maybe you can see too. Okay. Also, is there any preference to increase the, yes, font increase? We can increase the font too. It's not 10. I think 18 is okay. Off. I think we cannot increase the font. I hope you can see the font on screen. Okay, let's start with this CMS. CMS is the symbolic term, okay? We know we try to find the P critical force, therefore just only one unknown available. Therefore, I want to these P forces is symbolic. Okay, so I write the CMS of P. This is, I think that this is a little bit working slow. I think that. Yes, extremely slow. I'm waiting the result. I think I give a like 5 seconds to wait to respond. If the, it's, I think that it's causes due to internet speed to other things. Okay, I think I can use my desktop version. Also, you can use a cell phone. Cell phone version is working much more efficient at this internet version. Also, you can download the cell phone version. Okay, I want to continue with the desktop version. I write CMSSP. So eccentricity is given 200. Also, C is given 105. Also, we have a K value. K is equal to 0.5. And sigma y is needed. I don't know the sigma y. Is it given or not? I think it should be given in here, but I cannot see. Where is it, sigma y? Where is it, the sigma y? I forgot to write the sigma y. It should be, is a, yeah, we use the same type of column. I think that 250. Yeah. No, I can say that. I can say, also I can add this thing. Okay, right, sigma yield stress is equal to 250 MP a megapascal. Okay. So I don't want to use this term. I want to continue. Okay. So sigma yield is, I'm on GY like this, 250. And one more two, yes, Rx is also needed. Where is the Rx? Rx is equal to 89.9. And where is the and sigma y? Area is needed. A is equal to 7,560. Look at the formulation. Is there any term is missing? Yes, modulus of elasticity is needed. Where is the modulus of elasticity? Oh, again forgotten. I think that I remember that modulus of elasticity. Also, I can write to 200 gigapascal. So I need to convert to the megapascal. I am working with the Newton millimeter. Therefore, I have to write the E is equal to 200,000. Yes, 200,000. Okay. Rx okay. E okay. C okay. Sigma Y okay. Every okay. Every term is okay. So I want to write the R function, nonlinear function, like P divided by, in parentheses, sigma Y times A multiply by our big parentheses 1 plus A times C time divided by Rx square times in second. I can't remember a second defined is MATLAB or not. Okay, I will control this. Second K times, oh sorry, I forgot to also write the L as in here. Also L is equal to, we're working with the millimeter. What is the value of the L? In our question, L is equal to 4 meter. Therefore, we need to convert the millimeter 4,000. Okay. Go back to our equation. Yes. Right in here. K times L divided by, in parentheses, 2 times Rx out of parentheses times square root in parentheses E divided by E parentheses A times A. Good. So after then I will need to convert to the inline function. These after these terms, if you're familiar with, if you want to learn something same about the MATLAB, I want to give a little bit detailed information about the MATLAB. If I define the one term is a symbolic, the other term is the constant, is f becomes a symbolic terms. Why are we helpful about the symbolic terms? You know, it's, you can see a little bit confused function. We can take derivative, integration, the other things, but in order to solve this equation system, unfortunately we have to convert to f as a function. So inline helpful about to convert to a function from the symbolic term. Therefore, I want to use the f equal to inline f. I want to assign again to convert it to f value. Therefore, f becomes f inline function. Now f becomes the inline function. After that, f0 helpful to compute to result. I don't know, to maybe I can give a 500 for it. It's f0 is a helpful to find the root of the function. Okay, and f0 is the I think if I use the parentheses, like what is the half, you know, f0 is the fun. We rewrite the function now, and x0 is the also is the initial guess. Therefore, I want to write the our function name is f. Initial guess is the, I want to write the 500. After that, oh, it's terrible. I think I made a mistake. I'm sorry, I forgot to put the minus in here. Oh, yes, all term is okay, but I forgot to put the minus in here. Therefore, I have to rewrite in here. Hopefully, copy paste and helpful for me. And I put a minus in here. And again, f and line f. Now I will use the 500. And after that, I obtain like different result. I think that maybe I made a mistake or not. I don't know. Sometimes we have made a mistake. Okay. and the result is the 5, this is the kilonewton, this is the Newton, therefore, and result is, I don't know which one is correct. The alternative, you can check my hand calculations or write in the equations if you have time. You don't have any time, okay? You can use it this is the Newton. If I divide it with this is the Newton version. If you divide it with the 1000, this is the kilonewton. 518 kilonewton. I don't know, and also my calculation, MATLAB 419. Which one is correct? I don't know. But maybe we can look at and we can check our result. Maybe I made a mistake in somewhere. Maybe I made a mistake in when I solving this part. It's up to us. I don't know. Okay, we will see. Okay, never mind. I say that this is very complicated, easy to make a computational mistake. You can see I made a mistake, but I hope you learn two strategy how you can use a nonlinear equation, solve a nonlinear equation on MATLAB. I hope you will understand. Okay. Now I can pass to the next question and next subject there. And in inelastic buckling, up to this point, we are always talking about also ideal column. We always say our structures have the elastic case. So also we are comparing the yield stress. If to pass to the yield stress, we say that our systems will collapse. But actually, in material properties, after yielding stress, we will material is not collapse and continue to carry loading. Therefore, in practical case, especially in our standards, we are always also consider our structure after our material, when the material pass to the yield stress part. So also, but if we consider in this case, our computational seems a little bit complicated. But we can use a simplified two formulations to inelastic buckling and formulations to buckling load, critical load, and inelastic buckling related to this statement. Okay, and also long slender column, especially long slender column, pre-critical due to buckling is much more important. Sorry, critical for in first case, mostly critical obtained from the buckling, therefore yield is not very important. But intermediate and short columns, especially and for short and intermediate columns, yield stress is much more effective than the buckling load. Therefore, we can also consider the buckling load, so we can also consider the yield in that for intermediate and short columns. So I don't want to give you more information. I think that we can directly pass to the solution technique. It is very not complicated. It's very easy techniques. If we have first of all to lambda PL, maybe you remember the lambda. Lambda is the slenderness ratio, Kn over R. Our lambda value is smaller than the plastic limit value, lambda PL, which is equal to P squared E over sigma PL. Sigma PL meaning that yield stress, okay? I think I don't like to write the yield like, I can write like this, yield stress is okay, much more understandable. And yield stress, if I lambda PL, okay, P critical load is also occurred from the buckling. We call this the elastic buckling case. We will use the previous equation, and that's P squared EI KL over L squared. But when our lambda is smaller than lambda PL, elastic slenderness ratio lower than the plastic, then we will use the new formulation, just only change the modulus of elasticity term. We call this ET, and is the modulus of elasticity for plastic case. We compute the ET and we calculate the critical load by using this formulation. Just that. Just we compute the lambda, we compute the lambda PL, compare with if first case happen, it's okay, no problem. If second case happen, we will find the additional modulus of elasticity and we will compute the sigma critical load. Okay. Let's start with the, solve with the example 13.4. We have a sigma epsilon diagram, stress strain diagram is given, okay? And also sigma PL, meaning that to yield also plastic limit case. I think that I don't need to use the sigma y, like sigma PL is okay. You don't need to confuse the yield stress like this, okay? And PL is given in here, okay, 150. Also 270 is also second changes of the ratio of the modulus of elastic term change, okay. Now our solid element have a 13 millimeter diameter. Diameter is 13 millimeter as a solid rod. That is a cross-sectional circular cross-section we have. Also length is given 600 millimeter. This made the material can be modeled as strain diagram is given. If it is used, the pin supported column determine the critical load. So both ends is pinned. In other words, K is equal to 1 and determine the critical load. First of all, I want to compute the epsilon values for using the strain diagram. First of all, I start with the first line. You know, in order to find the first line, epsilon sigma PL 150 to the minus 0 divided by 0.001, and after that, I find the modulus of elasticity is equal to 150 times 10 to the power 3 megapascal or 150 gigapascal. In second case, in order to using this line, I have to subtract 270, subtract from 150, subtract 150 from 270, and also 0.002 minus 0.001. And after computing this, also not A, sorry, this should be 18. I made a little mistake in here. 80 in here. Okay, this megapascal. Now I will calculate the radius of gyration. You remember the radius of gyration is square root I divided by A, and after that, you know, P, you know, modulus of elasticity of the, I'm sorry, moment of inertia of the circle shape. Maybe you remember or you don't remember. Maybe I can to remind you that on circular shape, moment of inertia Ix equal to Iy, it doesn't matter. P R over the R to the power 4 over 4. The area, you know, P R square. In question, R is equal to 0.15. You know, diameter is given. Radius is half of diameter. So I read the formulation. I get the radius of gyration is equal to 7.5 millimeter. Also, I can compute the cylinder illustration. I say the both ends pinned, therefore K is equal to 1. L, you know, to 600 divided by R, we obtain the 80. Now we plan this plastic cylinders ratio limit. So I write this lambda PL, you remember the P square A over lambda PL, and all after that we compute the lambda PL is equal to 99.31. So which cases occurred in first and second case? I think that lambda is smaller than lambda PL. Therefore, we will use the sigma critical P square E2 KL over R square. So after put values, sigma L is equal to P square ET. We write the values. We obtain 2. Sigma critical is 185.1 megapascal. After that, P critical is equal to sigma critical times A. So we obtain the P critical is 130,808 Newton, also 130 kilonewton, as I can say. The correct result. Okay, And this is the last subchapter of the chapter 13, is a critical load in design practice. Up to this point, we are always talking about the theoretical information, but in practical case, we have a simplified formulation taken from the standards. I want to take to for still LRFT AS, the American standard. Also in Turkish standard, we have the same formulation because we directly adopt this formulation from the American standard. Therefore, these formulations are almost same. Maybe you will have a, are you taking or not a still design course? We are familiar with this design course. Okay, nominal axial force, critical force is the A times F critic, is also a sigma critical load. Maybe you can use like symbolization is a little bit different American standard. You know, in American standard, American standards, F is used instead of sigma stress value. Sigma C, also lambda critical, lambda C is critical, lambda is computed from the like this formulation, K over R, P, sigma I over L, like this formulation. Okay. And also sigma, this value is smaller than 1.1 is the critical. As if smaller than 1.1, sigma critical computed from this formulation. If greater than 1.1, sigma critical is computed from this formulation. That's it. You know, this is the sigma critical. If you compute with the gross area, we can obtain the nominal point force. For reinforced concrete, the computation strategy is different because it's a composite structures form aluminium and wood structures. Formulation is very similar to American standards, but some kind of the safety factors, these some of the coefficients a little bit different. Just I want to put to steel design code formulations. Just very similar formulation. If you form by using formulation, we can easily obtain the critical force for due to the compression. Okay, let's start with the again A36. You know, remember the elastic property. A is equal to 200 gigapascal modulus yield stress is equal to 250 megapascal, and also cross-sectional property is given, and using the LRFT standard determine the largest load it can safely support. Okay, first of all I want to compute the lambda C. You can see is lower than the 1.1, and therefore I want to use this formulation. And after using this formulation, we obtain the sigma critical load. After computed with the sigma critical load multiplied with the area, we obtain the nominal force. Just it, not complicated, very easy. Also, graphical illustration is helpful about. You can see this is the inelastic backlink and inelastic backlink. You know, it's elastic backlink case and inelastic backlink. In here, there is a some kind of 1.1. Our lambda C is greater than 1.1. We call this the elastic backlink formulation. Is greater than 1.5. You will use the inelastic backlink case. Okay. This is the last example of our chapter. I hope you understand clearly. Sometimes due to my English speaking style, I have a little bit trouble, especially speaking on microphone and computer screen. I have trouble. But if you have any private question, you can ask me as on email. Also, you can send me on message on the team and also classroom. Any way you can use it. See you on next chapter. Bye bye.